The most powerful magnetic fields we know of are not in laboratories, not in particle accelerators, not even near planets or ordinary stars. They live in objects only about 20 kilometers across, spinning dozens of times per second, whose crust can crack with a jolt that briefly outshines an entire galaxy. These are magnetars and quasars, engines of extreme cosmic power that the James Webb Space Telescope is finally letting us study in unprecedented detail. To understand magnetars, start with a massive star that has died badly. When a star more than about 8 times the mass of the Sun exhausts its nuclear fuel, its core collapses under gravity in a fraction of a second. Protons and electrons are crushed together into neutrons, forming a neutron star, a city-sized sphere with more mass than the Sun, so dense that a teaspoon would weigh 1 billion tons. Most neutron stars already have strong magnetic fields, trillions of times Earth's, but a small fraction are born spinning so rapidly and with such intense internal turbulence that a dynamo effect amplifies their magnetic fields to truly absurd levels. In a dynamo, moving conductive fluid generates magnetic fields, which then influence the motion of the fluid, creating a feedback loop. Inside a newborn neutron star, superdense nuclear matter and superfluid neutrons swirl violently as the star settles. If conditions are right, this motion winds up the magnetic field like a spring, boosting it to around 10 to 10 times Gauss. For comparison, a fridge magnet is about 100 Gauss. The strongest human-made magnets reach around 10 Gauss. A magnetar is 1 trillion times stronger than that. At such strengths, the magnetic field is no longer just a background. It becomes the main character, dominating the star's behavior, and even the structure of the vacuum around it. In these fields, quantum electrodynamics, the theory of how light and charged particles interact, starts doing strange things. The vacuum becomes birefringent. It behaves like a crystal that splits light into different polarizations. Photons can turn into electron-positron pairs and back again. The magnetar's crust, a rigid lattice of nuclei, is locked to this field. When the field slowly twists or rearranges, it stresses the crust until it cracks in a starquake. The sudden reconfiguration launches alpha waves, disturbances in the magnetic field, that accelerate particles and release enormous bursts of X-rays and gamma rays. In 2004, one magnetar in our galaxy flared so intensely that it briefly altered Earth's upper atmosphere from 50,000 light-years away. From Earth, magnetars usually appear as faint, persistent X-ray sources with occasional violent outbursts. Traditional X-ray telescopes can measure their brightness and rough spectra, but they struggle to see the cooler, infrared glow from their surroundings. This is where JWST becomes crucial. Its infrared sensitivity lets us look for dusty debris disks around magnetars, the remnants of the supernova that created them, and for faint companion stars that might be feeding the material. By measuring how the infrared light is polarized, the orientation of its electric field, astronomers can indirectly probe the geometry of the magnetar's magnetic field and test those exotic quantum predictions about vacuum birefringence in ultra-strong fields. If magnetars are compact, local monsters, quasars, are the opposite. Beacons, visible across most of the observable universe. A quasar is powered by a supermassive black hole, millions to billions of times the mass of the Sun, sitting in the core of a galaxy. On its own, a black hole emits no light. But when gas, dust, and even stars spiral in, they form an accretion disk, a flattened, rotating structure where friction and magnetic turbulence heat the material to tens of thousands of degrees. This disk shines across the electromagnetic spectrum. Close to the black hole, twisted magnetic fields can also launch relativistic jets, narrow beams of plasma moving at speeds close to light that extend for hundreds of thousands of light-years, injecting energy far beyond the galaxy's central region. Quasars are so luminous that a single one can outshine all the stars in its host galaxy combined, radiating up to 10 hours times the power of the Sun. For decades, we mostly saw them in optical and radio light, as bright points with broad spectral lines from fast-moving gas. But the early universe is full of dust, and dust is very good at blocking visible light. Infrared, however, can slip through. JWST's infrared instruments can see quasars at redshifts greater than 7, meaning we are looking back to when the universe was less than 1 billion years old. Their light has been stretched by cosmic expansion from ultraviolet and visible into the infrared. By dissecting that light, JWST can measure the temperature and composition of the dust, the speed of gas in the accretion disk, and even estimate the mass of the central black hole. This matters because quasars are not just spectacular fireworks. They help shape their galaxies. When a quasar is active, it can drive powerful outflows, winds and jets that push gas out of the galaxy's central regions. Gas is the raw material for star formation. Remove or heat it, and you can shut down the birth of new stars. This feedback helps explain why massive galaxies today are often full of old red stars and relatively little cold gas. JWST has already observed quasar-host galaxies in the early universe that show signs of intense star formation and strong outflows happening at the same time. It's catching galaxies in the act of being transformed by their central black holes, giving us snapshots of how the tight correlation between black hole mass and galaxy bulge mass may have been established. Magnetars, though much smaller, also inject energy into their environments. Their flares can ionize surrounding gas, stripping electrons from atoms and changing how that gas cools and collapses. In some cases, magnetars are suspected to power fast radio bursts, millisecond-long flashes of radio waves that release as much energy as the sun emits in days. If that's true for at least some bursts, then magnetars are not just isolated curiosities, they are part of a broader ecosystem of high-energy astrophysical phenomena. JWST can't see the radio bursts themselves, but it can examine the host galaxies of these events in infrared, measuring their star formation rates and dust content, and testing whether magnetar formation is linked to particular kinds of stellar nurseries. Put together, magnetars and quasars are like two extremes of the same story: how gravity and magnetic fields, acting on very different scales, can tap into the energy stored in matter and light up the universe. Magnetars show us what happens when a stellar core collapses into a quantum object where nuclear physics and relativity collide, and magnetism becomes almost unimaginably strong. Quasars show us what happens when entire galaxies feed their central black holes, turning gravitational potential energy into radiation that can regulate the growth of cosmic structures. And JWST, by extending our vision into the infrared and back in time, is turning these once abstract monsters into detailed physical systems we can actually model, measure, and compare. Yet even magnetars and quasars, for all their drama, still live within the familiar fabric of space-time. To push the idea of extreme cosmic power even further, we have to ask a stranger question. What if the fabric itself can store and release energy in ways we have only begun to imagine?